Hi, and welcome back to Elementary Statistics. I am moving on into Chapter 4, and we're working on probability. So the first things we're just going to talk about are how probability works and the different ways that we use it. And I'm going to show some examples, and I'm going to try and tie it into things you might have worked with before. And we will talk just a slight amount about odds and how they are different than looking at probability. So some of the basic terms that we have to get to know, we have to make sure that we know that the event is the result or what we're trying to find. An example of an event could be when you have a deck of cards and you're playing maybe blackjack, and the event that you're trying to get is you're trying to get 21, so you win. So the item that you're trying to get, if you have a 6-sided die and you're trying to roll a die, the event could be rolling a 6 or rolling a 4, whatever you're trying to get when you're working on something. A simple event is an outcome where it only has one option and it can't be broken down into other components, and the sample space are all of the options that you have. So here we have an example talking about a child, and so if we're having a baby, we have choices. Well, not a choice of what we're having, but when we have a baby, we can either have a boy or a girl. So that's a simple event, having one child. Now, if we have multiple children, and in this case it's looking at 3 births, in the right-hand column we have all the options. There are 8 options. You could have a boy, 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 and so now we're also bringing into account in what order they were born in, and then we can have a boy, boy, girl, and so on. The simple events would be the ones where we have boy, 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 or girl, 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 because those ones, there's only one way that's going to happen. But when you look at having 2 boys and a girl, or if you're looking at having 2 girls and 1 boy, there are multiple ways for that to occur, so those are not simple events. They're still events because there's still an outcome we're looking at, but they're not simple because there are multiple ways to do it. Some of the stuff that we have to make sure we know is that when we are looking through the textbook or coming across probability in other areas, a capital P along with some type of a letter is meant for probability. And so we can see that we have P of A here, and it's saying the probability of that event occurring. Now, somewhere they would have to define what A is. So sometimes what you'll see is that, if I grab my pen here, they'll do something like A is rolling a 1, B is rolling a 1 or 2, and then they'll say what's the probability of A, what's the probability of B. So that's one way you might see it. Another way you could see it is they won't actually use the letters, and they'll just say what's the probability of rolling a 1. Now, they also would need to tell you what exactly you're rolling. So am I rolling a 6-sided dice? Am I rolling a 12-sided die? What am I working with? That all has to be informed too. Probability only occurs between 0 and 1. 0 means that it's impossible to happen. 1 means that it's going to happen no matter what. And then there's all of the variation in between. So one instance might be if you're rolling a 6-sided die numbered 1 through 6, and I said what was the probability of getting a 7? Well, you can't get a 7 on a 6-sided die numbered 1 through 6, so that probability would be 0 because it's impossible. But if I said what's the probability of getting a 1 through 6, a 1, a 2, a 3, a 4, a 5, or a 6 on a 6-sided die, that's certain to happen because one of those answers fits in my event that I'm trying to get. Probability can be written down as you see here, so all values will fall between 0 and 1. How you find probability, there's 3 ways that will be defined here, but try and think of it as in the most uncomplicated way. So in the event, let's talk about on this one, the event of flipping a coin. So maybe I'm looking for what is the probability that I will get a head when I flip a penny. So my probability of A in this case, I should have wrote A there. Well, on a normal coin and a penny in this specific instance, a head is 1 out of 2 sides. So number of times the A will occur, well, it can only happen once, and number of times the procedure has been repeated, well, I flipped it, and I can only have it, there's 2 options that are there. So this way is another way of thinking about it. We can make sure that every option is equally likely to occur. That's part of the criteria. So on the flipping a coin, a head is as equally likely to occur as a tail. On a regular 6-sided dice, the probability of rolling, let's say, an odd number. Well, on a 6-sided die numbered 1 through 6, your odd numbers are 1, 3, and 5. So there's 3 options out of the 6 sides of the die. We do want to make sure if we're writing it in probability that we would reduce any fraction that we have. Sometimes you'll also see it as a percentage, and sometimes you'll see it as a decimal. When we're dealing with scenarios, sometimes it's not feasible for us to, for instance, flip a coin 1,000,000 times, or sit and roll a dice 1,000,000 times, or even money-wise go out and talk to a situation. There's also the ethical bounds that if we're dealing with medicine or another psychological event that could do some trauma. So we use simulations to do that instead. And one example is a random baby simulation that is out there. And the idea behind the random baby simulation is that in a hospital, if the tags weren't on the babies and so you didn't know who belonged to who, you would just give a child back to a parent. What's the probability that the parent would get the correct child? And though ethically we would never do such a thing, we would use a simulation to show what that is. And there is a simulation out there. I'll put it on the website if you want to look at it. That is obviously something we wouldn't want to do in life, and so we definitely want to do it with a simulation. When you're dealing with probabilities, if you are going to change them into decimals that aren't exact, you should do 3 significant digits. I will put a page also on underneath this section 4.1 that gives you the rules for 3 significant digits. The law of large numbers just says that if we do an event over and over again, eventually the experimental probability will become the theoretical probability. So if we think simply of flipping a coin, I know that I should get a head half of the time. So if I flipped it twice, one of them should be a head. If I flipped it 10 times, 5 of them should be a head. Well, if you sat here and did that real quick, you might figure out that, well, I only got 1 out of 10 that was a head, or maybe you did better and you got 7 out of 10 that were heads. The law of large numbers says, though, if you do it enough times, so maybe 10's not enough, maybe I need 50, maybe I need 1,000 times, but if I did it that many times, eventually I would end up that I get heads half of the time and I get tails half of the time. If I roll a 6-sided dice and I do it enough, I'm going to get every one of those numbers 1/6 of the time. So if I did it 60 times, they'd all occur 10 times. If I did it 600 times, they'd all occur 60 times, and so on. So we'll just do a little bit of probability here. So in recent years, there was about 3 million skydiving jumps, and 21 of them resulted in death. What would be the probability of dying when you skydive? So if we think about it in terms of how many times or what we're looking at, so we're looking at dying. Oops, I forgot to grab my pen. So it would be 21 times that we would die out of total times jumped. Total times jumped was 3 million. So the fraction or the probability of that, so the probability of death when you skydive is 21 out of 3 million, which reduces to 7 out of 1,000,000. Can leave it like that, or if you want, you can change it to a decimal. Here's an example talking about texting and driving. In a study of U.S. high school drivers, it was found that 3,785 texted while driving during the previous 30 days, and 4,720 did not. Based on these results, if a high school driver is randomly selected, what would be the probability that he or she texted while driving during the previous 30 days? So the top number is the event that you're looking for. So we're focused on the probability that they texted while driving. Well, 3,785 were texting while driving. Now the thing here though is the bottom is the total. And there wasn't 4,720 total. What there were was 3,785, because that's how many were texting, plus 4,720. That's how many were not texting. So I'm going to grab my calculator. 3,785 plus 4,720. So they actually talked to 8,505 students. So that is approximately 0.445 or 44.5%. So if you randomly selected a high school student that was driving and asked them if they texted, 44.5% of them approximately will have texted in the last 30 days, according to this probability. A compliment is the opposite of what you're asking for. So in the instance where we're talking about skydiving and dying, the compliment would be not dying. In the instance about texting, the complement would be not texting, so it's the opposite of what you're talking about. So here, if we were talking about what's the probability of not dying, we don't want to use the 21, what we want to use those that did not die. So we're going to take 3 million minus the 21, so 2,999,979 people did not die out of the 3 million. So that would be the probability of not dying, because we did the complement. When we start talking about probabilities, how they're going to help us later on is we're going to find out the probability of something occurring, and we're going to compare it with what we call an alpha level. And we're going to try and find out if it is significantly higher or significantly lower, less or greater, depending on which terms you want to use. It is common practice to use what we call a 0.05 alpha level or probability, and it's not rigid. Sometimes we'll use a 0.01. I've seen a 0.10 used. It depends on how important it is. Usually medical experiments and examples use a 0.01 because it's critical that we make sure it's not going to occur by chance. The one thing I didn't comment about but was on the one slide before, that when we talk about P of A, that is what we're looking for, and when we put a line over the top, that is what we're not looking for. So the difference with odds that we have to make sure we're thinking about is that when we talk about probability, it's what we're looking for over the total. So probability, oh, I don't want that. Let's get rid of that real quick. I just want to keep focused on the basics. So probability is the event over the total. That is different than odds, because as it's motioned here, and you have odds against and odds for, but when you're dealing with odds, what you want is what you're looking for based over what's not what you're looking for what its complement. So you can see that you'd have to actually add the two together with an odds to get the total. So something simple, we'll try. If it was maybe 3 out of 5, we'll say that was the probability of getting an event, then the odds would be 3 out of 2 or 3 to 2. Because if there's 5 total and 3 is what I'm looking for, then 2 is what I'm not looking for. So be careful when you're dealing with odds versus probability. So go ahead and take a look at your assignment, do the ones that you can do, and let me know if you have any questions. Have a good night.